What's pulling the Milky Way? We do not know what it is. This is a true cosmic mystery. The pull is slow, a gentle but persistent tug across unimaginable distances. It spans millions of light years, a cosmic current in the vast ocean of space. This force moves entire groups of galaxies, vast cosmic flotillas sailing toward an unknown destination. Our own home, the Milky Way, is caught in this flow. We are passengers on a galactic ship. We are moving towards something we cannot fully see. It is a motion so grand, it redefines our place in the universe. Scientists watch this motion with great care. They are like cosmic cartographers, trying to map the unseen currents of the cosmos. They study detailed maps of space, plotting the positions and movements of countless galaxies. Their goal is to find the source of this immense pull. The cause is not yet clear, and the search for it has led to some of the most profound discoveries in modern astronomy. The journey to understand this cosmic drift is a journey to understand the very structure of our universe, from the smallest stars to the largest superclusters. We are drifting through space at over 1 million miles per hour. This is not the speed of our spin, our orbit around the Sun. This is the speed of our entire galaxy, moving relative to the background glow of the Big Bang. It is a peculiar velocity, a motion that is separate from the overall expansion of the universe. Think of it like a boat on a river. The river itself is flowing outward, but the boat is also being pushed sideways by a hidden current. We are trying to find what is making that current. The question is simple, but the answer is deep. What is pulling us? We all feel the force of gravity. It is the invisible tether that holds us to the Earth. It keeps the moon in orbit and pulls the ocean tides back and forth. The rule is simple. Bigger things pull more. Planets, stars. So it makes perfect sense that some enormous object, far away in the depths of space, could be pulling on our galaxy. But the universe we know is not so simple. It is a place filled with more than just the things we can easily see. The cosmos is full of mass, but not all of it shines. The mass is found in the brilliant light of stars, in vast clouds of interstellar gas, and in fine grains of cosmic dust. But most of it is in a mysterious substance we call dark matter. We cannot see dark matter with our telescopes. It does not emit light or reflect it. We only know it is there because we can see its gravitational effects. The pull on our galaxy, this cosmic drift, might come from objects we already know about. Perhaps it is a colossal collection of galaxies, a city of stars so large that its gravity reaches across hundreds of millions of light years. Or perhaps the answer lies in the things we do not yet see. The pull might originate from a vast unseen continent of dark matter, a hidden structure that is shaping the flow of galaxies across the universe. The challenge for astronomers is to weigh the universe. They must account for all the visible matter and then infer the location and amount of the dark matter. By doing this, they can create a map of gravity. They can predict how galaxies should move based on this map. When they compare their predictions to the actual observed motion of our galaxy, they find that something is still missing. The known matter and the inferred dark matter do not fully explain the speed and direction of our journey through space. Long ago, astronomers charting the motions of nearby galaxies noticed something strange. Galaxies shared an extra motion, streaming in the same general direction toward a specific point in the sky. This region, a gravitational anomaly, was given a fittingly dramatic name, the Great Attractor. The name sounds like it belongs to a single monolithic object, a cosmic monster pulling everything toward it. But the Great Attractor is not one thing. It is a vast region of space where the concentration of mass is unusually high. It is a sprawling metropolis of galaxy clusters, each containing thousands of galaxies like our own. The combined mass of all these clusters creates an immense gravitational well. It is this well that tugs on the Milky Way and our neighbours, drawing us gently but inexorably toward it. The pull from the Great Attractor is real and measurable. Galaxies in our local supercluster, including our own, are drifting toward that part of space at hundreds of kilometers per second. However, identifying the exact source of this pull has been incredibly difficult. The Great Attractor lies behind the plane of our own Milky Way galaxy. This region of the sky, known as the zone of avoidance, is thick with gas, dust, stars, which block our view in visible light. It is like trying to see a distant mountain through a thick fog. Even as our tools improved, allowing us to peer through the dust with infrared telescopes, radio telescopes, the Great Attractor did not tell the whole story. The mass that we could account for in that region was not enough. It could explain some of our motion, but not all of it. The speed of our drift was too high. It became clear that the Great Attractor was only part of the puzzle. It was a significant landmark on our cosmic journey, but it was not our final destination. A larger, more distant force was also at play. With the mystery of our motion deepening, scientists knew they needed a bigger map. They began to look not just at our nearest neighbours, but at the movements of hundreds of thousands of galaxies across vast stretches of the universe. By analysing how these countless galaxies moved relative to each other, a new and breathtaking picture emerged. They discovered our galaxy is part of an even larger structure, a cosmic supercontinent of galaxies bound by gravity. They called it laniakea, meaning immense heaven in Hawaiian. A fitting title for our home supercluster, spanning over 500 million light-years. It contains roughly 100,000 galaxies, all moving in a coordinated dance. The map of laniakea is defined not by what we see, but by how things move, gravitational flow lines. Scientists drew boundaries by tracing those flow lines. Everything that flows toward a central basin is part of laniakea. We live in one of its distant suburbs. The discovery gave new context for our motion. It showed that the Great Attractor is not a destination, but the gravitational centre of our supercluster. We are part of a grander flow within laniakea. The entire structure is itself moving, like discovering your city sits on a river, but the whole continent is drifting. Laniakea is moving toward the Shapley concentration, located about 650 million light-years away, the largest known collection of galaxy clusters in our local universe, a true gravitational titan. Flow lines extend from Laniakea toward Shapley. The picture: Great Attractor pulls us, Great Attractor pulled toward Shapley. But even this did not solve everything. Even with these magnificent maps of Laniakea and the pull of the Shapley concentration, some of our motion remains unexplained. When astronomers carefully subtract the gravitational pull of all known structures, all the galaxies, clusters, superclusters they can see, there is still a leftover velocity. It is a small but persistent motion that does not seem to point toward any known mass concentration. It is as if our entire cosmic neighbourhood is being swept along by a current that originates from beyond the known map. This unexplained uniform motion is sometimes called dark flow. The name is evocative, suggesting a mysterious current flowing through the dark voids of space. It implies that something else is at work, a force that we do not yet understand. The data suggests that a huge number of galaxy clusters, spread across billions of light-years, may share this peculiar motion. They are all moving together in a coherent direction. like a flock of birds flying in formation for reasons we cannot discern from the ground. If dark flow is real, it presents a profound challenge to our standard model of cosmology. One idea is that this flow is caused by the gravitational pull of structures that lie beyond the edge of our observable universe. Another, more radical possibility is that dark flow is a sign of new physics, or even the influence of other universes in a larger multiverse. These ideas are debated. Some argue dark flow is a statistical anomaly. The mystery remains unresolved. The questions linger. How do scientists measure these incredible motions across billions of light years? Well, the primary tool is light. When a galaxy is moving away from us, the light it emits gets stretched to longer, redder wavelengths. This phenomenon is called redshift. The faster a galaxy is moving away, the greater its redshift. This is the bedrock of our understanding that the universe is expanding. But a galaxy's motion is a combination of this expansion and its own local movement. To isolate the local movement, scientists subtract the motion caused by expansion. What remains is called the peculiar velocity, its true speed and direction through space, driven by gravitational tugs. A galaxy's peculiar velocity tells a story, whether it is falling into a cluster, orbiting a larger neighbour, or streaming along a cosmic current. By measuring thousands upon thousands of peculiar velocities, scientists build a three-dimensional map of cosmic flow, like a weather chart of the universe. Arrows point away from empty regions, known as voids, and converge on clusters and superclusters. These measurements are hard, small signals buried in expansion. They rely on precise telescopes, standard candles like supernovae, and even subtle patterns in the cosmic microwave background, each adding a piece to the puzzle. To understand these vast cosmic movements, a simple analogy can help. Imagine a perfectly calm, flat sea. This represents the universe expanding smoothly in all directions. Now, drop many small stones, each makes a ripple. Add a few large boulders and their ripples dominate. Our galaxy is like a tiny boat on this sea. Its motion is the sum of many ripples, pushed and pulled by currents flowing in different directions at once. The boat cannot easily tell which stone created which ripple that moves it. This is the Milky Way's situation. It feels the gravitational pull of many masses. Our local group, the Virgo cluster, the Great Attractor, the Shapley concentration. We try to pick apart these pulls to see if they add up. Some boulders may be hidden deep under the water. Likewise, like a massive crowd flowing towards stages and bright vendors, we may feel the collective push without seeing the source. We see the grand flow of galaxies, but pinpointing the ultimate source is monumental. Perhaps many sources, or one giant source just beyond our sight. There are a few main ideas that scientists are exploring to explain the unknown part of our galaxy's motion. The first and most straightforward idea is that the pull comes from mass farther away than we have mapped in detail. The universe is enormous, and our best maps cover only a fraction. A truly colossal structure could exist hundreds of millions of light-years beyond the Shapley concentration, its immense gravity tugging on us. A second idea, dark matter, is the key. Being invisible, it is mapped indirectly, from gravity's effects and lensing. Our current maps may be incomplete, with vast filaments or sheets channeling flows we cannot explain with visible matter alone. Enjoying this journey? Please like, subscribe and share. A third, more profound possibility. Our model needs revision. Perhaps gravity differs on the larger scales, or new physics is required. We simply do not know yet. Different methods sometimes reach conflicting conclusions. Signals are faint and errors loom. Scientists test this with galaxy surveys, the cosmic microwave background, and X-ray clusters. Each method has strengths and limitations. The lack of consensus is not failure. It means we are at the edge of knowledge, grappling with an important question. So, why does this cosmic tug-of-war matter so much? The motion of our galaxy is a powerful probe. It tells us about the distribution of mass throughout the universe and tests how structures grow over billions of years. If the unexplained motion is ordinary mass far away, we must map deeper. If it is new physics, our view must evolve. New observatories on the ground and in space, like the Vera C. Rubin Observatory, will map the southern sky, measuring properties of billions of galaxies. Increasingly, precise surveys will measure peculiar velocities and reduce uncertainty, filling gaps hidden by the Milky Way's zone of avoidance with infrared and radio views. The more complete the map, the better we can trace flows and pinpoint their origins. Each gap we fill makes the picture less mysterious. For now, the tug remains a captivating puzzle. We see the motion, we see the grand structures. Big things attract smaller ones. The full story is not yet written. The universe keeps its secrets, but not forever. Each new measurement, each new map brings clarity. One day we may point to a place on the map and say, now we know what pulls our galaxy. Until then, keep watching, keep measuring, keep wondering. What do you think pulls our galaxy? Did you like the video? Leave a comment and don't forget to like, subscribe and share.